sala and join us on the chairs here in front, just to let you know, and then we'll move them over to our coffee table of disorganization as it currently stands. Chip Shearer, who is going to be speaking last in our morning session, brought samples of the moon and Mars that you can touch. And so we will have those samples and he will have them. We'll move them around and keep an eye on them, but they will be over here on the coffee table if you want to experience that for yourself, which I strongly recommend. I already did it, so I'm good. So keep a lookout for those, but I wanted to let you know this is what they look like. So when you're milling about, keep an eye on that and have a go at it. So I'm going to turn things over to Anna Lobet, who is going to introduce our next speaker.
Welcome, everyone. It's an honor for me to, here we go. Yes, good. To be representing the J. Robert Oppenheimer Memorial Committee. For those who don't know about that committee, it was formed more than 50 years ago to honor the intellectual and ethical legacy of J. Robert Oppenheimer. How many of you know who he was? Yay! Yes, he was the first director of Los Alamos National Laboratory, and we have many scientists from the lab here today or online. And how does one honor the intellectual and ethical legacy? We do that by partnering with organizations like NMC to create a series like this one. And also, we organize the annual memorial lecture. It's going to happen here in Los Alamos on June 2nd. So pay attention to the pamphlet that you have in your hands, and you will see that Professor John DeBerry will be our speaker. We bring international speakers over to the New Mexico to propagate, to enhance science, communication, and knowledge. We also do that by funding scholarships for local students as well as students from other regional students, and we will honor those students as well in our annual memorial lecture. So stay tuned for it. And if you have friends and so on, please let them know. We are always open to new students applying for those scholarships. And one of the next speaker, Karl Hibbitts, is a research scientist from Johns Hopkins in the Applied Physics Laboratory. He's a planetary scientist working to understand the compositions of the surfaces of Moon, the Jovian satellite Europa, and other airless bodies in our solar system. He uses experimental as well as theory to try to understand what's going on in the processes in space. Dr. Hibbitts is also the deputy principal investigator in several launched events. You will hear about the Europa Clipper infrared mapping spectrometer, as well as hopefully you will also hear about balloons. In the previous lecture, you heard about how we explore space, sending things up there. You will hear from that. And I wanted to tell the students in the room that Dr. Hibbitts earned his BA in physics from Cornell University. Here we go. Then a BS in geology from the our own University of New Mexico, and he got a PhD and a master's degree in geology and geophysics from the University of Hawaii. So it's been around the block. John.
All right. Thanks a lot. And it's been a fun journey. Like one of the other presenters say, it's really the journey that counts. So if you haven't figured out your directions in life, in fact, I hope you haven't yet, have fun doing it, right? And on this, so today I'll be talking about, and thanks for the invitation, by the way, it means a lot to me. Appreciate it. We're going to be talking about the moon and achieving a sustained presence on it, what that's going to require. Whether we do it in the next 10 years, the next 50 years, there are certain things that are inevitable that we're going to end up doing. That's going to be using the resources on them, first on the moon, and then learning how to do that so we can go to Mars, right? And that's where our eyes really are, is heading to Mars. But moon is what's in the sky right now. And I think, to paraphrase engineer I used to work with back in the V2 project, if God wanted us to be a spacefaring nation or have a sustained presence in space, he would have provided us a moon. And he certainly did. And you're watching the video right here. It's not just inspiring. Everybody sees it, right? Everybody on the world sees the moon. So it is incredibly inspiring, but also it happens to have the right characteristics that almost makes it inevitable that we'd be spacefaring nations because of where it's located, how it affects the Earth, and where the resources are, and what the technology is that we have to develop in order to use those resources so that then we can go on to Mars. It's almost a perfect situation that we have there. So what you saw here on the slide coming just previously was the near side of the moon. You saw the dark patches, the mare. That's where lava flowed, very similar to the lava here in New Mexico that you have, right? And then the moon rotated and zoomed in onto the South Pole. And we are looking at the South Pole here, and the near side is now up on this side. The far side's here, because you know the nearest side is always facing the Earth. And this is an important slide simply because you see some bright regions. These bright regions are areas where the moon is almost constantly illuminated, so that one can land near there and be adjacent to areas that are constantly not illuminated. And there may be resources, we think there are, there's evidence for some of it, but we don't yet know yet. And I get to that in the talk a little bit. Oh, okay, thank you. This is better, guys? All right, thank you. I'm holding it because it's easier than having to not move. I like to move when I talk. So the ridges are really important because we can use those for a power supply, and so that we can then access interior craters right there, right? So before I get on into talking the talk, let me talk a little bit more about myself. Yes, New Mexico was a foundational experience for me, actually. I came here after serving the military, and I wanted to go into planetary science. And it was my first course with Jim Pike, who was running the Institute for Meteoritics. His course on the moon that really got me interested in working on the moon, as well as more into outer space. And I actually worked with Shearer and somebody else right there that we know very well. We met. We're the same as, say, academic age, I suppose, yes. Yeah, so it's really been a lot of fun. All right, so what do I do now? I do a lot of laboratory work to look at the properties of materials that are analogous to what's in outer space, and also analyzing materials from outer space. I also, as you heard, am involved with the mapping imaging spectrometer that's going to Europa. It was launched in just last year in October 10th. It'll arrive in 2030. So some things take a long time. And then one thing you like about the moon, guys, is the moon is close, 3 days away, not 30 years away. However, speaking of which, I'm also involved with the Lunar Surface Innovation Consortium. In case I forget later, I want to mention it now. Institutions should think about joining this if you haven't already. It gives you access to the government, private industry, nonprofits, academias who are all interested in developing technologies for enabling sustained presence on the moon. So we haven't the capability yet for a sustained presence, right? We can barely land on the moon yet again. But companies, and it's just a fact, right? But companies are already thinking about what we're going to do next and develop the capabilities for what will be done next. So this is open that to participation. So I encourage you to join it. These are squiggly lines and stuff I won't talk to too much because this is what I like, but you know, I'm going to keep this a little bit higher level. This is a artist's rendition of what a base on the moon could look like. It's not very realistic because everything's on the surface and it's going to be exposed to the radiation of space that you really can't shield from. But the important point here is the solar illumination that you just saw swirling around. The sun at the South Pole is going to be no higher than 1.5 degrees off the surface of the moon, and that makes it quite challenging for maybe operations. But also it makes it quite useful for solar power because you only have to put up your array, and it's always going to be, the sun will always be circling around you. So quite amenable, which is one of the major reasons going to the South Pole. Instead of the equatorial region where the sun rises and the sets every 2 weeks, you have 2 weeks of darkness on other parts of the moon. Here, certainly of the South Pole, you might only have 2 days of darkness. Well, there are a few periods where you have 2 weeks. Mostly you have like 200 days of sunlight. Kind of like the Arctic in the summer where the sun never sets, but yet the season doesn't change either. So it's quite impressive. So this is the moon. But we've all heard about, well, let's go to the Mars as well. So why moon first? Why not direct to Mars? And it's important to talk about that. You know, why not Mars first? And there's some very good reasons why not Mars first. There's some very good institutional reasons I'm going to talk about first, and these have existed for decades. And this is NASA's position, and there's really 3 pillars that NASA builds its lunar and science exploration on, and these include inspiration. The moon is, of course, very inspiring, as I talked about, very inspiring to students and everybody else. We all see it. It's great for STEM work and developing science leadership. It is also technologically achievable. The technology we need to operate on the moon is something we're already developing, so we can continue down that path as well. And also, there's a national posture. We have to admit there is competition as well as collaboration in going after the moon. Can't ignore that fact. So we all want to succeed as a nation and personally. And being one of the first, again, to put astronauts back on the moon is something that's driving the country. And it'll probably continue to do so even more now, which is fantastic. But what's really new, and that's really pushing us forward even more than that, and which is actually enabling, is the fact that industry is now potentially getting involved. They see the potential value and are developing themselves their own technologies for enabling access to the moon and potentially even doing commercial operations there. Importantly, in a very responsible manner. That's something that we need to keep in mind as well, that any activity we do on the moon needs to be done very responsibly, right? But for the first time, the moon may be in this what's called the economic sphere of influence, a term I think was coined by John Marburger, if I get his name right, back from the VSE days, right? The idea that now the moon and cislunar space, the space between here and the moon, can be in an economic sphere. We can actually utilize it, not just Earth orbit, but out there. Companies like Blue Origin, SpaceX are thinking in terms of that, but also smaller companies, Intuitive Machines, and a whole bunch of smaller companies, all are beginning to base their technology and business models a bit on Earth applications, of course, because there's not yet money on the moon, but they have their eyes on the moon for the future, even as we have our eyes on Mars as the future. So Mars is a little bit different. Mars is much further away, right? It really is outside this potential sphere of economic influence, at least for the next many decades. It is about 200 times as far away from the Earth as our moon is, and as such, it takes a much longer time to get there. A few days to the moon versus 6 months for Mars. You probably, in most cases, have to stay on Mars for several months in order for the moon and Mars system be in the right position to come back in a reasonable amount of time. And another reason the Mars is a little bit more challenging is that it's because it's further away from the sun, solar illumination is about 2.25, 2.5 times worse or less than on the Earth, or less than on the moon, and a little bit less useful. And so nuclear power may be needed, which is certainly feasible. Fission surface power exists out there, but it's a little bit harder to propose programmatically. So NASA and industry has really been focused on the moon. This, I think we know about the Artemis Accords and the Artemis signatories. There's well over 40 nations now that have signed on to this whole program of going back to the moon, collaborating, and so has, and in fact, China has a similar one as well. And so we're going forward on that. And the Artemis architecture includes, getting people back on the moon, and then transitioning to industry slowly for a sustained presence there. And how is this achieved is really the crux of my talk. And it begins with several missions. And I have this slide up here to remind myself that it's not just NASA that's moving down that path. DARPA has just released an announcement of opportunity. So it's not, they are interested in enabling activity in space as well. They're proposing a low altitude spacecraft to measure water on the surface of the moon at a scale that I'm going to get to here, which would be very enabling for industry to take the next step to do to do a more detailed reconnaissance. So we're already on our journey of a gradual transition of lunar activities, first by NASA and then to industry. And as students now, you'll be able to participate in this for many years on end, because this is going to be a very slow journey. We have yet to really land successfully on the moon in a meaningful fashion. I would argue this is going to be a decades-long process. But it's occurring, and it's going to be part of a much larger lunar architecture, which is kind of schematically shown here. That's going to include a lot of very interesting technologies that each of you may be interested in. So that's why I put this up there. Many of you may be engineers interested in things like precision navigation and timing for accurate repeat landings on the surface of the moon in areas that where you want to build a base. You have to land in the same spot over and over. How do we do that safely? Very interesting. You want to have to dig things up, acquire materials and transport them. This requires a lot of engineering as well as understanding the moon. Going to require different science and different engineering. Going to use robotic assets. While I'm not talking about the use of robotic assets, that's going to be a very big opportunity for people in the future, for scientists and engineers. Activity on the moon is inherently going to be limited by human presence. In other words, humans are squishy. We aren't designed to live on the moon. We're designed for the Earth, right? Robots are much better suited for that, yet they aren't really capable of doing everything we want to do. How do we make them more capable? How do we operate them through telerobotic operations? Maybe virtual reality, model-mediated operations. It's going to be wide open. There's a lot of work there, especially the AI and machine learning to add in the capabilities. All with a couple of current technology like vertical arrays to build the capability to dig up what's on the surface of the moon. Don't need too much of it, and process it so that we can use it for sustained presence. And why do I keep talking about resources? Why are they so important? Well, this all gets back to fundamental physics of why one of the major challenges of space exploration, and that is getting off the Earth gravity well, right? While this isn't the focus of my work, this is really the reason why we care about resources on the moon. Currently, if one is to get off the Earth with a rocket, you have to bring enough fuel with you to do that. Then you get into space. And if you only have enough fuel to get in space, well, that's fine. You go to the moon or you go to Mars, go in the solar system, but then you can't stop. So you now have to bring enough fuel so you can stop. And if you want to land at the moon, not only do you have to stop at the moon, you then have to land at the moon. Then if you want to come back home, you got to bring enough fuel to come back home. Each time you have that requirement to bring that fuel, it goes in this equation, and it gets bigger and bigger. You need to bring more fuel. Your rocket has to get bigger. You have to bring more fuel to take that off the ground, and so forth and so on. So it becomes very economically prohibitive. Your rocket has to get huge, which is why the Starship is massive, because it has no other choice but to bring its fuel from the Earth, and therefore it has to be massively huge to do that. That is not just what we need. You aren't going to just bring an ocean liner or a tanker everywhere you need to go. You need to have stuff in between. And I'm serious when I say the word tanker. How many starships does it take to land on the moon? Well, it has to refuel between 10 to 20 times, depending on your calculations, to actually make that viable. That is, well, it's not crazy. It will probably get done. It can happen. But it's not the way to have an economically sustainable presence on the moon. For that to happen, we need another solution, right? We don't want this. So what is that other solution? I've already been talking about it. It's learning to use the resources on those bodies to basically refuel yourself. And this is non-trivial. As we say in science, it's decidedly non-trivial. It is hard to do. We haven't figured out how to do this yet. But we have no other choice. Therefore, I say it is inevitable. It may not be soon. I'm hoping it's soon. Blue Origin actually thinks it's going to be soon, and they're talking about it. Blue Origin has a lot of money. They've put a lot of resources, money resources, into enabling these resources. So what are these resources real quickly? Well, if you look at the moon, which you do every day, well, whenever it's not cloudy, it's not cloudy here much. The moon really doesn't have much on it. This is Jack Schmitt on the surface of the moon, Apollo 17, playing around in the dust. He's getting dirty, but the dust itself is really the resource on the surface of the moon. It's one of the resources I'm going to talk about. Also, as I mentioned, there is water ice. We just don't know how much and where it is. For reference, we're already understanding how to use the resources. China is sending a mission soon to do some preliminary work to understand the nature of the regolith, and also to look for water ice and begin to the process of understanding using the resources called in situ resources utilization. Technologies developed here can be applicable to Mars as well. These are pictures from Viking as well as Perseverance and Insight, which actually did dig up some dirt and show, I should say regolith, and show water ice, which sublimed away, as we talked about, under vacuum, very low pressure, water ice just sublimes away. So resources are there, and they're useful. And these are the resources, and these are how they're useful. The regolith itself is probably the most useful. Unfortunately, it's also the hardest to make usefulness out of. Whether it's Moon or Mars, this dirt, or the Earth, in fact, this dirt contains iron and calcium, but more importantly, oxygen, and silicon's useful too. Oxygen is the oxidizer used in propellant. Rockets use oxygen to burn the fuel that they bring with them. The fuel is either hydrogen or methane or kerosene, but usually it's going to be hydrogen or methane when we go back there. 80% of the weight of a rocket fuel is oxygen if you have hydrolox, if it's hydrogen as your other component. So it's the oxygen you really care about. Water contains both hydrogen and oxygen, but at least regolith contains a lot of oxygen. Also contains important mineral metals that you can use. Why do we care about metals? You don't have to bring your rebar with you when you build your base on the moon, do you? No. You want to be able to actually use the moon itself, right? So it's fantastic. Unfortunately, also contains stuff we don't like sulfur. You know, sulfuric acid, not good. Sulfur dioxide, bad. So we have to figure out how to deal with the contaminants. The Mars has a lot of these contaminants. But by learning how to do this on the moon, we can then be able to do it on the Mars more effectively as well and go forward and as well. Now, ice, it's on both bodies as well. H2O, what can I say? It's fantastic. You get oxygen, hydrogen. We know how to deal with it. We know how to use it. Okay, we know how to electrolyze it. And also we can use it as drinking water. But it's a very important point. If there's only people that we cared about, we don't need to bring resources with us. Right? You don't need to mine the resource. You can just bring it with you. It doesn't take that much oxygen to live. We use about 1 kilogram a day, I believe. Might as well just bring it with you. And you can recycle some of the oxygen. You can recycle water. The driving factor for resource utilization is defraying the cost of operations there of wherever you're at, so you can have a sustainable presence. I would argue that Antarctica isn't sustainable because we have to bring stuff with us. Same for Moon and Mars, right? Right. So how are we going to make this work? Well, the first step, recon. Figure out where the stuff is. Well, we know where it is on Mars, more or less. We know the regolith is on the moon, so we don't have to recon for that. But we don't know where the water is. And this is a very important point. NASA often says, water first, water first. So they don't say that as much anymore, in part because of our messaging at the Lunar Surface Innovation Initiative saying, stop doing that. Okay, don't follow the water on the moon. We don't know where the water is. We don't know how much it is. We don't know its physical state. We need to do missions to find this out. And we should give our government some credit now because they are flying. They're going to fly this low altitude neutron mission to actually take the first step of finding out where that water is. Not the only step, but it's the first step. And then once we know where the stuff is, water or dirt, we excavate it, we process it. I make it sound so easy. And then we just store it, and then we use it. Not a problem, right? And there we go. So I figure maybe next March, we should be well on our way. But let's not forget the really hard part. And actually, this is the hard part, maintenance and repair. How are we going to fix this stuff when it breaks? Exactly. Hubble was unique and very interesting. It was designed to be repaired. When the astronauts there helped repair it, it's right there. It was designed that way. What lessons learned can we take from that and the ISS so that we do the moon right and do everything on the moon right so we have the same capabilities intrinsically? And robots clearly are going to be needed to do that. You're not going to have astronauts spending the whole time waiting for something to break, then go there and change a fuse. It's going to be much more robotic. And this, by the way, has already been done on the Earth. Liquefied natural gas plants, I would say mining facilities off the coast of Australia are fully autonomous. They use a Spot robot, from Boston Dynamics to monitor things and fix things on that without people. So it is definitely possible and very achievable. Yes, the moon is different. You have the dust. You have all these problems. But those, as we say as scientists, that's just engineering. It can be done. Okay. So where do we want to go on the moon? We don't know yet, but we're going to figure that one out. And wherever we go, it's going to be someplace where there's sun. Next year is where the sun doesn't shine. And we will find, and that's where where there's water, we will mine that water as well. First step is a global recon. Next step is going to more local places, doing rovers, as I said, which, by the way, already exists. There's a rover called Viper. It fully built. It would be capable of doing much of this. It's not yet flying. The mission technically has been canceled, but it still exists and can be flown if someone had the willpower to actually fly that, either to its existing site or somewhere else. We have the technology for that. Let me go back. And then finally, we take a rover like Viper again and actually determine the nature of this water ice so that we can then mine it and utilize it. And getting to the nature of it, this is where I like to talk about the science, because this is what I do. This is really not why there's reserves of water ice at the poles, if there is, but it's actually quite interesting. And it's important to understand so that we don't mistakenly think that this itself is a reserve. And we've all heard about the solar wind. Maybe you heard about the water on the moon that's from the solar wind, that the solar wind is hitting the moon and making water, right? Okay. The solar wind is made up of ions and electrons, but it's mainly ions that we care about, mostly of hydrogen. There's helium as well, which is important. Helium-3 is hitting the moon as well, which is useful. These protons hit the surface of the moon, and they form OH in the mineral because you already saw there's oxygen there. So you add hydrogen to it, maybe with some magic, make H2O, voila, you got water. Well, what really happens, that stuff's happening. Also, meteorites are hitting. Comets have hit in the past before. The point of this slide is that what counts is understanding each of these processing and understanding the relative importance of them so that you understand what your resource is and how you can mine it. Solar wind is such a low flux and low abundance that it results in water at the level of a few hundred ppm, parts per million. That could be useful if it was gold we were mining and we knew how to actually extract it. But at this level, we're looking for percents of water ice because that's a technology we know that we understand to extract. So that probably won't be a resource from the sun. However, comets that have previously hit the moon billions of years ago, that water is still there in these permanently shadowed regions. Much of the water is gone, but a lot of the water had migrated around and landed in these cold traps and been covered up by dirt. Without sunlight hitting it and without energetic particles hitting it, the water remains sequestered forever. Missions have, like L-Cross, have actually impacted into the South Pole and found up to 5% abundance there. We just don't know how common that is and exactly what the distribution is. So we need to map it. And there's some technology that actually was pioneered here by scientists here at the Los Alamos National Labs using neutron spectroscopy to do just such a thing. Neutron spectroscopy relies on the fact not of neutrons hitting the surface of the moon, but very energetic particle called galactic cosmic rays that are moving at billions of electron volts. They go in meter deep into the surface of the moon. They react with the surface to create energetic neutrons. These energetic neutrons are moving very quickly. And if you ever play pool, which I assume some of you do, when you hit one pool ball and then it hits another pool ball, the energy transfer is very efficient. Similar sized mass objects can transfer the energy to from one to the other very effectively. So when these neutrons hit hydrogen atoms that are in water, they transfer the energy as well. All right, they slow up, and therefore you get a whole lot of slow neutrons. So by looking for the ratio between the fast neutron and the slow neutron, and then mixing in the in-between neutrons we call epithermal, you can understand the abundance of hydrogen in the surface of the moon. And we know that the moon isn't going to have a whole lot of organics like carbon and hydrogen in there. So you can infer something called water equivalent hydrogen. This was first done back in '98 by, I think it was Bill Feldman 98, and one of his postdocs, Dave Lawrence. Dave Lawrence is now at the Applied Physics Lab, and he's flown many of these instruments to different bodies and have mapped the water on them, Mercury, as well as asteroids. And now we're going to go back to the moon within the next year with a low-altitude neutron spectrometer, this case not by NASA but by DARPA, and we'll be mapping that at very high spatial resolutions. While a neutron spectrometer is working in a way that you only have like, a few kilometers is high spatial resolution. Well, that's not bad. Right now, we're mapping the water at 50 kilometers on a side. 50 is 2,500 square kilometers. You're not going to the surface of the moon and using a rover to figure out where in that 2,500 square kilometer area you need a mine. But if you got 25 square kilometers, yeah, maybe so. Scale does matter, right? And so if this mission goes, and it looks like it most likely will, then we're going to have luck understanding exactly the ground truth of this water. Coupled with other measurements, such as surface measurements that measure the water on the surface, and this is an example of a Chinese rover that did that showed that the solar wind water is actually a very sufficient of an air, and we'll be able to understand some of the processes responsible for the water on the moon and be able to model where we need to go to mine this water. I'm going to skip through this and talk a little bit about why scale does matter and a little bit about regolith as well, because I mentioned before that's the easiest one to land on, but it's the hardest one to process. Scale is important. I worry about, honestly, I think we need to be sensitive about the moon because it is everybody's resource. Okay, it is cannot be owned by anyone. Outer Space Treaty prohibits anyone owning the moon, but they can own the resources from it. They can't own the land. So how much of the surface of the moon do we want to mine up? Well, doing some simple math, we're talking about football field size areas. This is not a lot of area, okay, that we're talking about. So we aren't talking about scavenging new open pit mining on the moon or anything like that at scale. These are small areas. And we should keep that in perspective when we talk to people. And that's true whether we're mining water or using the regolith itself, which is a much more difficult thing to do, but the technology for it actually is being developed. This is at TRL6, a technology readiness level of 6, for actually melting the regolith and getting oxygen out of it, or CO, and turning the CO into oxygen. It's a rather complex system, and the system itself is at TRL4. And this is a different process using molten regolith electrolysis, where you actually do melt the regolith, which is kind of insane, at 2,000 degrees Celsius. And then you run electricity through that, and you, as if it were water, and you extract the oxygen from that. But then metal comes out too. You get both metal and oxygen. Very powerful technique, and this is what Blue Origin is actually pursuing. This is an example of making oxygen. Those are oxygen bubbles. You get this off the web. Those are oxygen bubbles in near real time forming in this regolith simulant. So they're making this happen. Has huge challenges though in terms of feasibility at scale. So scalability, durability. Molten regolith is extremely acidic. It destroys everything. And handling it is very, very difficult. So water would be great. We need to find it. Molten regolith is being sued by industry, though, which means if they continue to pump hundreds of millions of dollars into this technology, and Blue Origin has put tens of millions of dollars into this as well, then, you know, that may work so that we can have the capability of building the infrastructure on the moon for a sustained presence. But I want to finish up with one other resource, and this could be, I want to say this could be potentially, and this is actually a motivating factor for one company, two companies to go back to the moon. This is helium-3 mining. This is, sorry, I should not have laughed, but but helium-3 has is origin from the sun. It is potentially used in fusion if you get that going, but it's also used in cooling for down to very cold temperature in support of quantum computing. The challenge here is scale, as I mentioned before. It only exists at 5 to 20 parts per billion. So if you need 10 kilograms per year, you talk about 5 to 20 billion kilograms of regolith has to be processed per year. So that has a challenge of scalability, as well as in that case, it does have to be mined from iron titanium regions, so on the near side. That would be seen from the Earth. So I have questions about whether that should be pursued, because the moon and Mars, they really do belong to all of us, and we need to pursue them in a responsible fashion. And it can be done. I think it is intrinsically green, this pursuit on the moon, because it is so difficult to get there, resources are difficult to use, that you will want to reuse them as much as possible, be very, very efficient. Unlike on the Earth, where we're going from one continent to another, you could be inefficient because, I mean, we're designed to be here. On the Earth, on the moon, we're going to have to be much more selective on what we do. So this will be the last slide. Thank you.
You can hang on to that for a while, Karl.
No,
You got
okay.
it's up to you. Whatever you feel good about. Questions? Yeah, here we go.
We know what resources led in Earth, right? The wars and the fights and stuff like that throughout history. So what is regulating our access or abuse of the moon resources? Do we have something in place? Can anyone go and do whatever they want in the moon right now?
Yeah, I should have paid you for that question. Thank you.
That's a great question.
If you're interested in participating in that, you can join an institution like the Moon Village Association. They look at the moon resource with the perspective of being good stewards of the surface of the moon. So to answer your question, we have the Outer Space Treaty, which says, you know, you can use a resource but can't own the moon. There's a Moon Treaty, which the U.S. did not sign on to. But I would say the best way to make sure we use the moon responsibly is to be the first ones to get there, right? Because then you set normative behavior and normative standards. And whether we agree with our behavior as much as we think it should be, I would argue that the other group that's going after the moon is even less cognizant of good behavior. And therefore, you know, we should get there first. And in a collaborative manner, by the way, which I would say the Artemis Corridor is collaborative.
I think this question kind of follows up on that and what you're talking about with the being responsible. And I kind of have three questions. It's a way of, or three different ways of asking the same question, I think. But about like, what is the scale of that resource utilization and extraction on the moon and Mars? Like, and is there a concern about changing the planets in a way that damages them and our ability to study them as they are? And the last way of asking that, which I think you just answered, is, are there any extraterrestrial environmentalists?
There are. No, this is a very good question, and that's kind of why I put up the slide yet. We do care about it. Planetary protection is something that NASA cares about. They generally think of it, people often think of it like protect our planet, but in reality it's about protecting the other planets as well. So yes, also scientists very concerned about damaging the environment of the moon, because that makes doing the science more difficult, right? They're very cognizant of that. For the moon, there's been an interesting proposal: limit human activity to the southern hemisphere and the South Pole. Leave the northern hemisphere and North Pole as kind of a national park, you know, because simply landing on the surface of the moon is going to release a lot of water. You land a big rocket, you got what, tons and tons of water that are produced. That water's going to land in the cold traps as if it's a man-made comet, human-made comet. It will affect the science, the surface science. All right, so what, right? We understand that. Scrape that off, look below it. Scientists will have to find a way to deal with human contamination on the surface of the moon. So the key is to be responsible and realize that we're going to have to work together, industry and scientists. Industry needs to understand they're going to have to work with us as well. Now, back to scale, very important question. As I mentioned, the amount of water that we need, if it's at 2% abundance, will mean if 100 metric tons is what we want, then we're looking at a few football fields worth of the moon dug up meter deep per year. All right, so not that big, unless if you're actually kind of extracting it from the moon itself. So these are large-scale operations from that perspective, but from the size of the moon, very small. And if there's one resource that's a few kilometers in diameters, that can suffice for several years. Because remember, we have no one on the moon now. We have no demand signal. It's going to be a while. So yes, let's be responsible, be inclusive, but realize we are going to start small.
Okay, one more question before we move to our panel.
Hi there, Melina Curvasanos from New Mexico Tech.
You're done, Chip.
Thanks for the great talk. I had a question. I know you said the processing of regolith is still in very fledgling stages. We don't really know how we're going to do that yet. I was wondering if there are any ideas how we were going to deal with the contaminants that you mentioned, like sulfuric acid, and how would you maybe transport it back to Earth, find some way to manage that on the moon? So
yeah, that's a very important point. So one man's waste, another man's gold. Because it's so expensive to bring stuff to the moon and also bring it back from the moon, anything that bring back from the moon is going to have very high value. So it's going to be like maybe special pharmaceuticals, maybe amazing solar panels. I don't really know. But it probably won't be raw resources. So when sulfur comes out, we'll find a way to use it. Carbon comes out, whatever, we'll find a way to use that just because we will need to. The technology is being developed now. Solid oxide electrolysis is being developed. These processes are on the cusp of working. Now, is that cusp next year or 10 years from now? I can't say, but it's getting close.
Awesome. Thank you, Karl.
Thank you.
I got too excited about the panel, and I don't want to forget Chip. How could I do that? Chip is unforgettable. So let's welcome our final speaker before we get everybody to get the band back together. I'm really delighted that Chip Shearer, come on up, Chip, so we can all take a gander at you. Chip has been really wonderful to work with, also as part of the organizing committee. Karl and I, again, met Chip back in the previous millennium, and it's really great to be back here working with Chip, talking about the moon exploration. Again, I want to remind y'all to touch rocks, not like grass, that Chip brought with us. And so thank you for everything and being a great educator and colleague. Go ahead.
Thank you very much. It's a delight to be here. And again, I'm Chip Shearer from the University of Mexico. Everybody just calls me Chip. And I knew when I was 6 or 7 years old exactly what I was going to be. I was going to be a linebacker for the Green Bay Packers. And my career plan didn't go quite as what I thought it would at that time. What I'd like to do is, this is kind of a prequel or an origin story, if you will, for Karl's talk. In terms of, we've been to the moon, and this is kind of the next human step. 50 years too late, but still 50 years after Apollo. So what I'm going to do is focus primarily upon Apollo, how that really fits into Project Artemis and beyond, primarily from the sample analysis and sample point of view. But again, I'm from New Mexico, I'm speaking in New Mexico, and what I'd like to do is discuss also the moon coming to New Mexico and how New Mexico has been involved and can be involved in the future of lunar exploration. Let me just, before I go to, my mother was a stay-at-home mom. My dad joined the Navy when he was 17, and he was a refrigerator appliance salesperson his whole life, really good at it. And I really never really knew how much they appreciated science. Didn't have a clue. When they passed away, I went to clean out their house, and this is what I found all through their house. Newspapers about Apollo 11. There were other magazines from Apollo 8, Apollo 17. So I just want to point out that science can reach out to a large group of our citizens who are really interested, as long as you present it in the proper format for them to get excited about. Also, with all the excitement about Apollo, the Apollo program for exploration of the moon was very short-lived. If in the summer before you were going to college as a freshman or high school as a freshman, Apollo happened just before then. The Apollo program at 17 would have been over by your senior year. So it didn't really last the whole time you were in college or high school. It was very, very short-lived. But what I'm going to show is just over that short period of time and preparing for Apollo, really how much technology really had to change and be modified during that period of time. Just illustrates from the first Gemini missions or the first Mercury missions in May of 1961, and you can see the Mercury capsule, the Gemini capsule, till we got to Apollo. The technology involved in getting to the moon that we invested in, both in terms of science, engineering, technology, and tax money to get to the moon. And this was, again, 9 years, 8 years that it took us. I find that just awe-inspiring, and that when we look forward to going to the moon and beyond to Mars, we do need to keep this in mind, that there really is a dedication that one has to make to move forward. Also, again, during that short period of Apollo, the technology and capability changed dramatically. Just shows just the evolution of surface capabilities in terms of mobility. This is two images in the upper two diagrams illustrating their LRO images of trajectories or traverses taken by the astronauts. The first one you can see, there's a 50-meter scale, and essentially the astronauts walked from the limb to the crater a little west. And that's kind of like walking from here to your car in the parking lot. That's essentially the capabilities that were available during Apollo 11. However, by Apollo 17, again, your senior year, we had J missions, we had mobility on the surface for 15, 16, and 17. So from this place here, you could drive out to the Jemez and explore the Valles Caldera. So there is so much technology invested in doing geology and exploring. Also, we had a variety of technologies with regards to precise landing. You know, we landed in the Sea of Tranquility on Apollo 11, a fairly flat, relatively flat area, where with Apollo 17, we landed in the Taurus Littoral Valley, and you can see all the mountains around this valley, and precision landing was really important. Also, some of you, many of us here are geologists, and so we had an evolution of surface capabilities with training astronauts to do geology on the lunar surface, and actually then on Apollo 17, sending a geologist to the moon. And this diagram just really, this image just illustrates the capabilities that when one has trained individuals to do and observe science or geology on the moon, the types of observations and mapping that one can do. Oops. The mobility particularly made a big difference on the, and technology made a big difference in the time, in the terms of how we could explore. These diagrams just show you the number of EVAs or the number of times astronauts were able to leave the limb and travel outside the limb. And with Apollo 11, it was 1 EVA. By the time you got to 15, 16, and 17, there were 3 EVAs on each. The EVA distances, as you can see here, were 100 meters or a little bit more than 100 meters, all the way up to almost 40 kilometers total. That also impacted the amount of samples that one could return, as shown on this diagram right here, in which for the total mass that one could return from Apollo 11 was a little bit over 20 kilograms, but for Apollo 11, we returned almost 120 kilograms of material during that mission. Again, the technology enabled EVAs to be much more extensive. The mobility allowed you to explore the surface and sample. Also, there was an evolution in sampling technologies from just collecting rock samples, shown here from Apollo 11 and 17. But later on, during the later stages, the J missions, we were able to do double drive tubes. We had deep drill cores on the surface near the limb. We collected samples in shaded regions, and we also sealed the samples in these sealed containers so that there would be very little impact on the samples by the terrestrial atmosphere, but also so we could preserve any of the potential gases that could be coming out of those samples, which was very important in terms of trying to evaluate indigenous volatiles and volatiles contributed from space. So what did we learn from Apollo? In addition to just developing the technologies so we could go and live and function on a planetary surface, we learned a lot scientifically. And only 3 examples, only 3 are shown here. The giant impact origin for the Earth-Moon system was derived from some of the samples that came back from Apollo. This concept of a lunar magma ocean right here came from Apollo, and the samples returned from Apollo. And this concept for the moon has been expanded to the Earth. What was the early Earth like? Was there a terrestrial magma ocean? And it's also been expanded to Mars and a lot of the other terrestrial planets. Also, there's a concept that eventually came from the samples and computational calculations with regards to a late heavy bombardment in which the moon was bombarded probably on the order of 4 billion years ago, long after it accreted and formed. And this has been extended to understanding the the dynamics of the whole solar system, in which perhaps the outer gaseous giants moved at that time, sending a wide range of material into the inner solar system, forming some of these large basins on the surface of the moon. And again, that's still being debated. Okay, Apollo 17 ended. That mission ended in December 1972. And NASA has been extremely adventurous with regards to exploring other planetary bodies and investing money to not only just plant the flag somewhere, but to identify important science that can be done on those planetary bodies, either from the surface or from orbit. And Voyager 1 and 2, that was launched soon after Apollo, are now making their way out of the solar system. The first man-made objects to do that. And it's just utterly amazing. Also, what we'll hear later this afternoon, the Mars Sample Return Program and mission is currently active. OSIRIS-REx just returned samples from an asteroid. And Psyche is on its way to an outer asteroid in the outer asteroid belt. But the moon is there, and as Karl mentioned, we are going back with humans again. And so the question, Karl pointed out several really technology steps and reasons and economic reasons for going back to the moon. But I just wanted to highlight, at least in addition to building a cislunar space economy, there are other reasons to go back, such as undiscovered regions of the moon. The Apollo missions essentially explored this little portion of the moon right here. There's so much more of the moon that we haven't explored with humans yet. And again, this is kind of along the lines of the total area, surface area of the moon is equivalent to North America plus South America in terms of that area. So if we landed a Apollo 11 spacecraft in the Rock and Roll Hall of Fame in Akron, Ohio, and landed the proper distances of the other spacecrafts, most of those would have landed in the Midwest. You never would have seen the Atlantic Ocean. You never had seen the Rockies. You had never seen the Pacific or South America or the Andes. So there's a lot of areas that are unexplored. Also, there are new environments that we didn't recognize early on, such as these permanently shadowed regions that Karl alluded to, that could potentially have resources associated with them. And these reach temperatures on the order of, probably 25 to 45 to 75 degrees Kelvin. They're really cold. And then, of course, there are other reasons that Karl had mentioned, primarily tied to developing a space economy that hopefully New Mexico can be further involved and engaged in. Now, we do have numerous missions that have targeted the moon. Some of these are LCROSS, GRAIL, LRO, LADEE, and of course Artemis 1. And there are numerous other missions proposed, both robotic missions and human missions. So we're kind of, again, on this new frontier of returning to the moon. Karl showed these two diagrams in terms of the path to the lunar surface, both exploring and setting up an infrastructure on the moon and going ahead and preparing for Mars. But what I really want, because I'm a sample person, I look at meteorites, I look at Apollo samples, I look at Mars samples, is integral to all of these steps is samples will be returned from really unique terrains that we haven't examined yet. So let's look at some of the initial targets, and Karl had a really great video illustrating this, and I'm not going to be so elegant as he is. Again, this is the moon as you see it in the night sky in the full moon. The Artemis missions initially are going to the South Pole, shown here. The next is a topographic map of the moon with the South Pole down in this area, and this is the far side. A very large basin called the South Pole Aitken Basin here, one of the largest impact basins in the solar system. And then if we turn this a little bit, this is the South Pole Aitken Basin shown here with the location of the South Pole that we're going to visit with the initial Artemis missions. There are permanently shadowed regions there that have a wide range of potential trapped volatiles associated with them. And these are the potential landing sites in the South Pole that we could be planning to visit in the future. Now again, we're returning to unique terrains. Some of these terrains shown right here are ancient terrains that are probably the age of the moon, 4.43, 4.35 billion years old. This is the largest and perhaps oldest impact basin on the moon, which may allow us to date the movement of Saturn and Jupiter during the earliest stages of the inner solar system. So, what's New Mexico's role in all of this? And we've been engaged and involved in several pre-Artemis programs that prepare New Mexico and prepare the sample community for the next step for Artemis. And this is essentially tied to what's called ANCSA, which the University of New Mexico was the lead institution, and I'll talk more about that. There's a program, the Solar System Exploration Research Virtual Institute, that the University of New Mexico is an important node within that, and it's called, of course, Casa Moon, Home on the Moon. And then the University of New Mexico has placed funds from the Vice President of Research's office to really involve and look at the Sustainable Space Research Grand Challenge that really tries to look at what resources and people are at UNM, how can we essentially combine those resources and then reach out to the national labs and reach out to the developing commercial sector in New Mexico. I just want to show this and again point out that the ANCSA program, which involved approximately 100 individuals, engineers, and scientists from early career to those people who walked on the moon, is between Apollo and Artemis, and therefore provides a sample community with a real link between, excuse me, between the past generation of lunar explorers tied to Artemis with those that, or Apollo, with those who will be involved in Artemis. This program was run as a sample return mission without the high costs of actually going and getting the samples. Within the wisdom of the Apollo community, both at NASA headquarters and sample scientists, they came up with a plan that, well, all these Apollo samples, we do not want to all utilize. What we really would like to do is save samples for future generations. As scientific concepts change, as technologies improve for the analysis of samples, we want these pristine samples available. So they had samples available from what was called this double drive tube collected during Apollo 17 and sealed in the sealed container and sealed on the surface of the moon. other double drive tubes that we had access to, which had never been examined, and then a series of samples that were collected on the surface of the moon. And once they were returned, they were frozen at, they were kept at 25 degrees Kelvin, or minus 25 degrees, not minus 25 degrees centigrade for 50 years. And so these were the targets. And these targets were to essentially engage the sample community in this sample return mission, conduct preliminary examination of these samples, involve an awful lot of young, early career people in this. And this is just one of the initial photograph we had taken with me. And right in here is Harrison Schmitt, the Apollo 17 astronaut, who was a contributor, a great contributor to this. This involved a number of universities in the U.S., including the University of New Mexico, which was the lead university, and then a variety of universities outside these initial groups, and both international and foreign, and a bunch of national labs and NASA centers. This just illustrates where the sample came from. This is a LRO image of the Taurus Littoral Valley. The sample came, the double drive tube sample came from right here, which was in a landslide deposit that slid off the South Massif, and we don't know when that event happened. This also shows the Lee-Lincoln Scarp, where there may have been tectonic activity associated with it, and the other light spots here are where the frozen samples were derived. This is just a compilation. This right here is where that sample was taken. This is a compilation of images. There it is right there. And we're traveling along the Lee-Lincoln Scarp, produced by the Goddard Space Flight Center from LRO images. And it just gives you a real feel for the terrain that the astronauts operated in during Apollo 17. This is just an image of Gene Cernan and Jack Schmitt collecting that sample. And this
That's in bag 522.
Yep, there's Gene Cernan pounding in that double drive tube that, again, was sealed for 50 years.
Copy that, Jack.
Until we opened it.
Okay, I think I got it.
And Jack's
I think I got it, Bob.
I'm not sure how
Okay.
many of you know Jack, but Jack's voice is just so distinctive from Gene's.
And Jack, when you get done with this French, you...
ANCSA was in action with regards to processing the samples. We processed them in nitrogen. We went ahead and conducted a wide range of analyses on those samples. And we also, in those sealed samples, we teamed up with the European Space Agency. I've got 6 minutes here. What's that? Oh, I'm sorry. I'm sorry. And this is, we teamed with ESA to build this gas extraction and piercing tool. And we utilized this on labs that you could not put on a spacecraft at all. This is a Beamline and Argonne National Labs. These are cars shown here, so you can see some of the facilities that are available on Earth to make these measurements are incredibly huge. Also, we used new technologies. For example, this is the core image that was taken prior to opening in the early 70s, or the mid 70s. And this is a CT scan, or XCT scan, that we have here, that you can see. You can look at this whole core in incredible detail, which allows you to identify where samples are that one may want to extract and how to open that. The core sample vacuum container and piercing tool is shown here. And let's just see if this works. No. So what did we learn from the Artemis Science and Engineering? This was the first core sample vacuum container ever opened. There are only 2 collected, one on 16, one on 17. There's still one open for future generations. It's the first examination of a sample through a landslide deposit. It completes some of the experiments that were initially proposed by Apollo 17 science group. The first Apollo core opened since the 1990s. The first examination of Apollo samples frozen for almost 50 years. And we discovered a wide range of new rock types that you did not find in the rest of the Apollo collection or the lunar meteorite collection, which does illustrate the real diversity of rock types on the moon and the magmatic processes occurring on the moon. With regards to Casa Moon now, this is, again, as I mentioned, centered at the University of New Mexico. Our focus is on the origin, evolution, and chronology of the ancient lunar crust, the impact history of the moon in shaping the lunar surface, and therefore probably very early on the Earth's surface. We're involved in the origin, evolution of volatiles and their ISRU capabilities, like growing plants in lunar regolith, processing lunar regolith in terms of 3D printing, and then preparing for Artemis. We look at these samples from orbit and from the regional to planetary scale, all the way down to the nanoscale. These are just the team members at the University of New Mexico shown here, and the team members that are also associated with this survey node, all the way from Frankfurt, Germany, across the United States to Perth, Australia. We have a lot of individual facilities associated with this team. The New Mexico Meteorite Museum at UNM, which if you haven't been to, come see. It's absolutely spectacular. And a wide range of brand new technologies that were not in existence during Apollo. The Casa Moon has also had different levels of outreach, ranging from the seminar series, which is the Planetary Sample Seminar Series that reaches out to communities within the United States, but also has a wide group of international individuals who are involved in this. We are involved, at least on campus, this Moon Art Project to really illustrate there is a creative link between STEM sorts of activities and art. And it reaches out to a much broader community than just the STEM community. And again, of course, we were involved with probably a few thousand people within the 2023 eclipse in New Mexico. Now, the Sustainable Space Research Grant, or Grand Challenge, shown here, involves taking a large group of faculty and staff members involved in space research and integrating their efforts. And these are just some of the types of tasks that are involved in the sustainable space research, including the bottom line, aid in development of a New Mexico space economy that will benefit the citizens of New Mexico. And these are the potential opportunities that exist for students, if you're students out there, or faculties at other universities or your colleges that you can be involved in. And then finally, the moon comes to New Mexico. We are having the NASA Exploration Science Forum on the UNM campus at the end of July. And I invite all of you to attend. We're trying to raise some funding right now to essentially provide video or Zoom access to this meeting to the broader community. And then finally, the future is here right now. Join us. Thanks.
Oh, you keep the microphone, Chip.
Yeah,
We
I
have
got it.
Q&A. Yeah, you almost self-destructed.
Yeah.
I was wondering what that button sounded like. Questions? I love a moon tour. We got one. Colin gets to.
Hi, my name's Mike Breyer, just a layman interested in this stuff. But you mentioned just really briefly the idea of using 3D printing on the moon, using samples, and how that works. And can you talk a little bit about where that technology is right now and where that's going?
I don't know that much about it. We have a very large team at the University of New Mexico with fairly large 3D printers, and they're essentially looking at building they're just starting to look at simulants, lunar simulants, Martian simulants, to utilize those and to really see what is the most appropriate simulants and regolith samples, or lunar and Martian soil samples, one can utilize to do that sort of printing. They're looking at that. So again, as Karl mentioned, it's so important for going to the moon and building an infrastructure there and eventually moving on to Mars, that we are able to eventually live off the planet, if you will. And this is just one small step to do that. And again, we have another member of our group, another group within CASA-Moon that is also using these lunar simulants to essentially grow plants. And one of the groups has had New Mexico chili grown on the space station. And they're growing tomatoes now. And so in a few months, we're going to have New Mexico salsa there.
Thank you for this is this working? Yeah.
Yeah, I can
Thank
hear
you for this lovely talk. You know, so appropriate for the New Mexico Consortium to be sponsoring this event, as so much has been done in New Mexico. And I feel, being a native New Mexican myself, oh, by the way, I'm Galen Gessler, retired from from Los Alamos Laboratory. Just as I felt as a young graduate student when a New Mexican scientist was doing geology on the moon,
yeah.
Harrison Schmidt. But something that worries me, you know, in terms of New Mexico's involvement and our country's involvement in the moon, is the fact that the most recent lunar samples have been returned by China, and China is doing extremely well with rovers and so forth. The first exploration of the far side of the moon and so forth. And I was a little bit alarmed when Karl said that we'd better get there first because we know how to do it right. I'm not so sure, given certain current circumstances, that that's in fact correct. And I see China leaping far ahead of us, and they may well have the same attitude that they better get there first because they know how to do it right.
Yeah. Well, two things I just wanted to mention about space research in New Mexico, and then also the Chang'e missions, sample return missions. For Chang'e 5, which was in a small portion of the moon, that sample return mission was previously proposed to NASA here. And so they essentially imitated what that mission was. And then also the Far Side mission, that was a mission that was proposed to NASA called Moonrise, which I was a deputy PI. So at least right now, two of their missions, their sample return missions, they're essentially mimicking missions and the science rationale that we had proposed. So again, as you mentioned, we do need to move forward, I think, a little bit more than we have in the past. Second, in terms of you're a New Mexican, you care about New Mexico, and I think too much our students think they're in the backwater of what's going on in technology and space. And our group has developed a slideshow, and eventually will be a video show that really illustrates the New Mexico space heritage. And it's a really broad, very rich space heritage, starting from the Anastasies and making observations about the sun and the moon, through Goddard launching spacecraft in southern New Mexico, through New Mexico, UNM essentially examining some of the first Apollo samples, all the wonderful work that has been done up here to go to various planetary bodies. So we have a heritage, and a lot of our students aren't aware of it. And we are going to make them aware of it.
All right, thank you. No, hold on to that for a second, Chip.
Okay.
Thank you. So hold on to your questions. We're now moving into the panel session, so if I could have all the morning speakers.
Oh.
So we have Bryan and Matt and Karl, if you could come on up here and grab the microphone from Galen. Well, we'll work it out. And so now we have open questions from the audience if you have some saved up questions. And if you're able to kind of come to us a little bit more, that'll be helpful because we only have the 3 microphones and we're all sharing. So let's remind everybody who we are. And for fun, let's say your name and your favorite planet, and always embrace your inner rock star with the microphone. Like, just get up on it, right? Like, yeah, don't, but not Matt, don't lick it. It's always cheese on the inside. So for everybody, I'll start so you have a minute. And remember, that planet does not have to be in this solar system. What? So yeah, thank you everyone for the fun morning. I'm Lisa Danielson, your session chair. My favorite planet is the one I'm sponsoring, Uranus, not just because some people get really mad if you pronounce it any other way, but also because the ice giants are really understudied and they're extremely interesting, and that particular planet has been through it, and we do not know why. Why is it so crazy with its entire rotational properties in the solar system, fun moons, all kinds of stuff is going on there. So check it out in an appropriate scientific way. Okay, Bryan.
Name and then favorite planet. Bryan Butler. I'm at NRAO here in New Mexico. Well, not to steal Matt's thunder, so to speak, but Earth, of course, for me, because, well, duh.
I'll take this one. Yeah, go ahead and pass.
Yeah, I'm Chip Shearer from the University of New Mexico. And you want my favorite planet?
Favorite planet, please.
I bet you could guess. Well, not planet. Planetary bricks on it is the moon.
Nice.
Awesome. Karl Hibbitts, APL. Right. You know, the name doesn't matter, right? Rose would still smell just as sweet, no matter what we call it, right? So, you know, Pluto may not be a planet, but as far as I'm concerned, the moon is a planet. So if you picked the moon already, I still think the moon's fantastic, but also I'd add Europa. Already broken the mold.
Nice.
It is very interesting. It may actually have life in its subsurface, right? Very interesting moon. That could be the next talk.
Fun fact, while Matt's considering which planet he wants to pick, when the IAU was trying to figure out what to call Pluto and its friends, they wanted to call them Plutons instead of dwarf planets because they forgot geology existed. And so then they decided that wasn't going to work, and they were sad. Anyway, Matt.
I'm Matt Heavner here at Los Alamos at the lab at NMC and also at UAF Fairbanks. Number 2, my favorite planet is Pluto. Pluto is a planet.
When you're in New Mexico, we learned that today. When you're in New Mexico, it's a planet. It's fine.
I'm not as fashionable as Lisa, but my shirt does say a good planet is hard to find. Earth has to be. So.
Wow. I can't wait to see what the answer is for this afternoon's speakers. Great. So now we're open. I think we had a question that we didn't quite get to.
Hello. I am here today as a mom and a planet buff with my son. So I just wanted to say thank you because this was an amazing event to bring them to. But actually, I had like a 2-parter question. So one of the questions was about the chili in space. We actually have been able to meet that gentleman, and it was a wonderful situation about bringing culture into space and vice versa. And the second is, as mentioned in one of the, I believe, the gentleman in the white shirt, Karl, yes, thank you. So we went out into the constellation trailer, my kids and I, and one of the last presentations was discussing about what are we doing as a state and the recycle and the reuse of materials. And so a comment came forth just a little bit ago in regards to what are we going to be doing with the sulfuric acid coming back down. So my concept of like the whole trash issue here in New Mexico, how can we move, and maybe this is a somewhat of a question, a resource, a reuse, and I don't know where I could think of that, but my mind instantly went there, and that's probably for people much more intelligent than I am to figure that part out. But the concept of just maybe reusing what we have here and fixing a solution down in the planet and vice versa. So I don't know. That was just a comment, but my son actually has a really cool question.
Why do they call it Uranus?
Oh, I get to do that? Oh, aren't you sweet? This is one of those way back Greek gods kind of a thing. It just goes along. It's sort of like antiquity. You know, they want to pick something that seems majestic. Yeah, Karl has a great answer to talk about reusability, right?
To the
Sustainability.
reusability part of it, right? So you talk about reduce, use, recycle. So you talk about recycle, right? Recycle stuff on the Earth so we can reuse it again, right? I think that when we get to the moon, we're going to have things that are going to break. We're going to try to fix them, right? But they won't always be fixed. DARPA, they sponsored a challenge to look at recycling and reusing material. In fact, grinding up old spacecraft and using them to 3D print, using that metal, right? So it's very possible that some of the technology that developed on the moon can be transferable back to the Earth. And one of the examples that, in fact, is one reason why these private companies are looking at using regolith as a source of oxygen is that when you do that, especially with that process I talked about, not only do you get oxygen, but you get metal. So on the moon, you care about the oxygen and the metal. On the Earth, imagine we start with oxides. You care about the metal. You care about the iron you could get out of it. So we can come up with a way to basically decarbonize steel making, then you can make an impact on global warming and things like that. And it could be actually quite beneficial to them. So it's not just tying that the space program provided. We could potentially provide some actual help to the Earth. Yeah.
So the question about the chili is red or green or Christmas.
Go first?
You may.
Can you tell us what you need to do to be a planetary scientist?
Yeah. Bryan said you had to go to school for 24 years.
Well, first you have to be small. Well, for me, small. Relatively non-athletic, so I couldn't be a linebacker for the Packers.
It's not too late, Chip. I would pay cash monies for that.
Yeah. So that was the first thing. Second thing, I think our concept for planetary science and being involved in planetary science to some degree is getting broader and broader and broader. For example, I also collected rocks when I was little too. And so I approached doing football in college and geology in college, and also had considering a minor in art. And so, having a really broad base that you can really head in a variety of different directions. Also with regards to creativity is really important. And again, we're all tend to generally be focused upon STEM backgrounds, and that if you have a STEM background, that's what you need to be engaged in planetary science. That's not true at all. Being creative is really important, whether you bring it from a STEM perspective or you bring it from a art or music sort of perspective. In my node, Casa Moon, I just 6 months ago, I hired a metal band to essentially produce a song called Artemis. And it needs
Is
to be
there a
played,
link on YouTube for that?
and it needs to be played really, really loud.
Where can we find this? Don't just leave that
You
there.
can go to Casa Moon website.
It's on there.
But you need
Okay.
to play it loud. But these
Duly
are
noted.
actually STEM people at a bunch of California universities who formed a band and are approaching it in two different ways.
That's beautiful.
So a comment about the 24 years of school. So one of my faculty at Caltech was Jim Westfall, and Jim did not have a PhD. He only went to undergraduate. He was the PI of the what was called WIFPIC, the Wide Field Planetary Camera on HST. An amazingly brilliant guy, but he didn't go to school for 24 years. He got his undergraduate degree, and then he pursued what he loved, which was instrument building, essentially. And he was the PI with a group of others, of course, that built WIFPIC. And I think Chip is absolutely right that you don't have to have a PhD in physics or planetary science or something. We have people who do planetary science who come from all sorts of backgrounds. So, if it's your love, if that's what you want to do, that's what you should do.
So the last question was, how do I be a planetary scientist? And I'd say you all are. Earth is a planet. Open your eyes, use your senses, think of the Earth as a planet. You don't even have to look up. Looking up is bonus. But if you want to be a planetary scientist, you all are. Make observations, put stories together, think about the Earth as a planet. If you want to get paid to be a planetary scientist, that's a different question. I'm not going there. But
I want to go there real quick, though. Brought a really good point, Brian. What a planetary scientist means is changing, right? NASA has always funded them, but now we're in an era where possible industry is going to be leading our return to space to some extent. So one might actually become a planetary scientist, not through the traditional way, maybe not with a PhD, but actually work for a private company, be a scientist for that. Who knows where the future is going to go? My point is just know it's a possibility. Believe in yourself, just know that it's a possibility, and keep your eyes and mind open.
Hello. I remember hearing in the talks on the moon, one of the big challenges to a sustainable human presence is the processing of regolith. And I was just curious is there any possibility for microorganisms or engineered microorganisms to assist in that processing process?
Nice.
Yes. Yes, there is. NASA has funded work to do exactly that, to bioremediation of lunar regolith simulants to look for the, to basically get iron out of it and potentially oxygen. It has its own challenges, of course. One is that, it's kind of slow, right? We want to have a certain rate. So you have to look at this from a system perspective. What is my goal? What do I really need to achieve to accomplish that? What are my limiting factors? And then question each of those and go forth. So yes, it's possible. Maybe you'll be one who find out a way to make it work.
So I just served on an unnamed NASA review panel, and an unnamed proposal from an unnamed group included sending microorganisms to help with the 3D printing process. So you can actually facilitate the 3D printing by including these microorganisms that self-replicate. So you don't need to send a whole lot of them. So there's a lot of fantastic ideas about this kind of stuff out there.
So we spend millions of years evolving to be able to survive on Earth, right? Something I haven't heard this morning is living out in space exposes life to radiation, cosmic rays. In Earth, we have the atmosphere and the magnetic field, right, that kind of protect us. So what are we doing to, what are we thinking about? How are we going to, how is life as we know it, humans, right, going to survive out there when our own cells are going to be affected by cosmic radiation?
Yeah, there are a lot of people thinking about this at Ames and APL and others, but Karl did address that, so I think I'm going to turn it over to him.
No, I did not address it. I mentioned it, yes. It is not addressed. You know, NASA has programs that work with it. TRISH is the name of a program. They actually look at the health effects of humans in radiation environments, right? So I can't answer that question. I don't know where it's going to go, but you bring a very important point, in which I think I talked a little bit. So humans aren't designed for space, right? But we can design robots that are designed for space. And so in the lieu of only putting humans out there, you maximize robots and maximize the interaction of human and robots so we can optimize and, again, maximize performance of humans in space. Whether these humans are on Earth or actually in space can be somewhat immaterial. There's a time lag, but if you're remote, you're remote. But actually human alteration by a radiation environment is, that's going to be really interesting.
And so for the students out there, if you are interested in that topic, so Karl mentioned that one program, but the long duration human spaceflight studies are all, that information comes from the International Space Station. So if you just go through journeys and investigating International Space Station, long duration human spaceflight, there's a ton of biomedical research on what that's like and what that does to people. Because you're right, space is always trying to kill us. So this is a good planet.
Can I add one perspective to that?
Yes,
one,
Matt.
One thing about the moon is that we're still fairly protected by Earth's magnetic field. And so that's, Mars is much more challenging because then you're exposed to the solar wind. And so that's another reason, baby step to moon first, and Earth. Stay on Earth and enjoy your ice cream. But the moon is less harsh from a human biology, but it's still a hard challenge. Mars is even harder.
It is, and I learned from heliophysics review in this past year, the moon doesn't protect us as much as you would think, right? Because the solar wind isn't just like a uniform thing. It has arms like a spiral galaxy, so it swoops by us. And, I mean, it's great. It's kind of like a vacuum cleaner of debris material, like physical asteroids, et cetera, but it's kind of scary. Oh, go for it, Chip.
And also, in addition to those sorts of dangers, and one issue with the space station, but also a long duration flight to Mars, are things like bone loss that astronauts will encounter that can be very, very severe.
On that happy note, oh, we got one up here.
So Paulo Nomic with the Space Shrine Consortium. So for all of you, I'm thinking of space resources throughout all the presentations today, and I'm thinking of the next economic revolution. And several of you alluded to that, akin to agricultural revolution and the English Revolution with the Industrial Revolution. So I'm thinking of one place that I know in the United States that makes artificial analog regolith. Wouldn't be something productive to make our own New Mexican simulant regolith, and maybe UNM can work on it?
Well, again, just as a cautionary note with regards to lunar regolith, for example, the lunar regolith has many types of properties that are difficult to reproduce. And so most of the regoliths that are out there, they're regolith simulants, are usually trying to reproduce one or two or three of those attributes. And I don't think there's any out there that really reproduces them all. Is that right, Karl?
Yeah, I don't think there is either. Well, and then Karl will tell us things like iron nanoparticles and things that are super reduced because the Earth is full of oxygen. So chemically, it's extremely difficult to get the same thing. But Karl knows more than I do.
You guys are absolutely right. So to me, yeah. So a lunar simulant is to lunar regolith like computer models are to reality. They're all everyone's wrong. Some happen to be useful, and different models and different simulants are useful for mimicking different properties. And there's not one that does all of them.
And there actually are a number of simulant makers within the U.S. There's a group down at Florida that makes lunar simulants. The USGS has been involved in making lunar simulants. I think JSC, the Johnson Space Center, was involved in simulant making.
They were the keeper of the
and there's
recipes.
private companies right now. Yeah.
Yeah, it depends on what you want to do. This was such an amazing morning. I want to thank all of you. Thank you, speakers. Thank you, audience members, for all your lively and fantastic questions. Fantastic questions. Thank you, those of you who are viewing remotely. We have a lunch break now. And we also thank you for reminding me again. I depend upon you guys. We're a strong team. We have a lunch break, at which point, if the speakers are able to join us for lunch, students, you may have a chance to interact and ask more questions. We welcome your questions. And we'll have the Mars and Moon sample with us, right? Yes. And so you can interact with that and ship. Tell everybody the magic trick that you can do.
Oh, I'll tell them that.
There you go. Come to lunch.
I won't tell them until they
listen to. Yeah. Okay. That's it. Okay. Thank you.
Yep.